I am Anil Kumar. Welcome to my series on combinatorics. We have discussed many concepts. Now it is time to prepare for the test. So we talked about Pascal's triangle, then we understood how it is related with binomial theorem, and then we related with the binomial coefficients, and we learned about the combination, right? NCR. We talked about pattern rules and also the method of induction to prove a particular formula. Now, in this particular video, we'll analyze a situation and use all those methods to solve the given situation. So, it's all about diagonals in convex polygons. I hope you find it interesting and useful. You can always contact me on this email or at the website as you wish. Now, the question here, which we are looking into, is how many diagonals will be there in a convex polygon? Well, polygon could have n number of sides, right? So we'll try to prove this in different ways. It's a very interesting and extremely important question from examination point of view. As you know, a polygon with n sides will have n vertices, correct? So here, let us take a polygon. Let me call this as polygon A, B, C, D, E, right? So these are 1, 2, 3, 4, 5 vertices, correct? That also means 5 sides. Okay. So it's a pentagon. Okay. Now, connecting any two vertices will give what? Well, it could give either the edge of the pentagon or the diagonals, correct? So as you can see very clearly, what we have here is these are the edges, 5 of them, right? And then if we try to connect from point A to the other points as shown here, we get the diagonals. So connecting any 2 points, that is the vertices, we either get diagonals or the edges. That's very important to understand. Now, what happens if I add a new vertex? The number of diagonals will definitely increase, but by how much? Now we are saying here they increase by n plus 1, right? Let's see. How do they increase by n plus 1? Now let us say that we have a new point. Let's call this as a new point. Definitely, as soon as you have a new point, then the side or the edge becomes a diagonal. So we have one additional diagonal. So we have the side AB as an additional diagonal. So one diagonal has been added. On the other hand, from N, we could actually connect the points E, D, and C. Well, A and B will not give you diagonals, they will give you edges, right? So these are the edges, but then we get 3 more diagonals, right? Plus 3 diagonals. Do you see that? So in case of a pentagon, we get 4 additional diagonals. Likewise, you can do your research and you'll figure out that this is n minus 1, which basically is 5 minus 1 is 4. Is that clear to you? So basically, this particular side, which was the end, edge, now is a diagonal, correct? And then we got those 3 additional diagonals. So we have 4 additional diagonals when a vertex is added to a pentagon. So you get an hexagon, but that is what a change happens. So with this in mind, let us adopt different approaches and see how we can find a formula for the number of diagonals in any polygon. Let's say polygon of 10 sides. How many diagonals will that polygon have? This is what we are going to answer, correct? So let's move on and see the first approach. The very first approach is by the method of combination, right? So let's try to understand this particular method of combination. Okay, so once again, when you have a polygon with n sides, we have n vertices. Joining two vertices give edges or diagonals, and polygon with n vertices has n edges. So we also know that, right? So we can now find the number of diagonals. Now, how do we figure that out? Well, the point is, how do you get an edge or a diagonal? So what we are doing here is we are connecting these points, right? So we are connecting these points. Likewise, we are connecting the points, correct? These are the points of the polygon which we are connecting, correct? So many points we are going to connect. So basically, what you understand from here that connecting two points gives you either edge or a diagonal. That means what? That means from n, choose 2. And what will that result into? That will result into h, or we can say plus diagonal. Does it make sense, right? So when we say n choose 2, will give you edge and a diagonal. In a polygon, we already know that the value of edge is n, correct? There are n edges. N choose 2 means n choose 2. Perfect. So this is equal to that plus the number of diagonals. Is that clear to you? So we clearly get our equation. And the equation is the number of diagonals is equal to n choose 2 take away n. Does make sense to you? Simple logic. So that is how we get our relation straight away. So the number of ways to choose two vertices from n vertices is n choose 2, NCR. The number of diagonals are NCR minus n, since we know that a polygon with n sides will have n edges, right? So the edges are n. So that's very clear. So that is how you get your formula, which is NC2 minus n. Is that clear to you? Correct? Now, look here. We'll try to simplify this particular formula, which is NC2 minus n. You know what NC2 is. N times n minus 1 divided by 2. Take away n, right? Take away this n. Take a common denominator, cross multiply. Minus 2n will be added there in the numerator. And then minus n minus 2n becomes minus 3n. And so you have the formula right there, n squared minus 3n over 2. You can take n common, divide by 2. So definitely n has to be greater than 3. The numbers which we are talking about are always non-negative, correct? So combinatorics, as you understand, we are only looking into discrete numbers, which are whole numbers, non-negative numbers. Is that clear to you, right? So the n value has to be greater than 3. Of course, you know, if you have a triangle, how many diagonals can you make? None, right? There is no diagonal in a triangle. Perfect. So we have understood that there is a neat formula which has been derived very clearly right here. So we know now that the number of diagonals is equal to n times n minus 3 divided by 2. Correct? Now, just look into this situation and just verify. You can also substitute n as equals to 3, 4, 5, 6 and fill in this particular table, right? So for the number of sides, you can calculate and then check. So clearly, we know for a triangle, there are no diagonals. But in case of a four-sided figure, there are definitely two diagonals, as you can see very clearly. Correct? These are the two diagonals, right? Now, if you have a pentagon, for example, then taking one vertex, you can join it with the other two. So get two of these. Now we can take the other vertex and join those two. Correct? So we got four now. and one more can be created, you can see, from this to that. So we got 5 diagonals in case of a pentagon. So when we're talking about the hexagon, we know we are going to add one side and see what happens. When you add a side, already we had these 5, right? So let's draw those 5 which we had, right? So let me just reproduce that pentagon right there, correct? So that you clearly understand what are we trying to produce here, right? So okay, so well, the colors are mixed up. Anyway, you got the idea. 1 2 3 4 and 1 5. So let me just okay, that's so you have those 5. Better still, let me use the same colors so that there is no confusion. So from this particular point, we'll take 2 in blue, and then with green from here, we'll take, right? So we get these, oh, I joined with the hexagon also. Okay, doesn't matter. So let's now add them up. And now with the next vertex, which is, we got this additional, one was already there. Do you see that? And then from the next one, here we have one more. Perfect. And then from the next one, we have one more. So we'll just add another color to this. So those are all the diagonals which you can make. And if you count them, you get the number 9 also. But here, what I wanted to say is, when I add a point, let's say we are adding this particular point here, right? Then what really happens is we get vertices which are, let me draw the additional vertices which you get because of this point. So one is, of course, that we have to join this point. Now this is an edge, this is not a diagonal. Do you see that? So when you have an additional vertex, we get these two as edges. Now, but what has happened is we got one additional diagonal right there. So side becomes additional diagonal. Do you see that part? Side becomes additional diagonal, and then you can actually join this point with 1, 2, and 3. So we get 1 plus 3, which is 4 additional diagonals. So you can see from here that 5 plus 4 is 9, and that is how it is getting created. So in pentagon, you get 5 minus 4 additional diagonals to get into that scenario. So I hope this concept is clear to you, right? Anyway, we got a formula, and with this formula also you can fill up this table to get the number of diagonals when the polynomial sides or vertices are given to you. Now, let's look into another approach for this particular calculation. Correct. So let us say you make all your polynomials and count the diagonals as we did, right? So we of course counted them for 3, 4, 5, and 6. We know there were 9, right? So, and then again you can do more of them. But anyway, if you use the formula which we just derived, which was not, which was what, somewhere here, right? So which is kind of like this. We derived this formula, not this one. So what he did was, okay, I didn't write the formula here. Here it is. Yeah. So we derived this particular formula in the previous combination case, right? So we had this formula n times n minus 3 over 2. So that's the formula. So based on the formula, you can fill up the number of sides for different cases. Perfect. Now, we'll look into the Pascal's triangle to get a rule. Do you see some kind of pattern? Well, I've highlighted here some numbers which are 1, 3, 6, 10, 15. You see this 1, 3, 6, 10, 15, 21, and 28. Well, they don't really match, but they are one more, right? So if I write this 1, 3, 6, 10, all right, and what is the next one? 15, 21, okay, 15, 21, 28, right? So what we notice here is that this particular diagonal, which is the diagonal 2, when you label it with the Pascal, right? So with this is 0, this is counted as 1, and that will be 2, right? So that particular diagonal, and the row is, you can see row and placement is the second one. Do you see that portion, right? So the second diagonal which we are looking at, which normally we may also call third diagonal, but looking into the nomenclature of Pascal's triangle, it is diagonal number 2. So that is the position which gives us the number of diagonal, one more than the number of diagonal. Do you see that? Corresponding to each one of them. So if n is 3, we have a position here which is actually on row 2, right? Do you see that? This is row number 2, not 3. And therefore, to identify this particular cell, we could write down a formula. It is n minus 1 C2. Do you see? I mean, choose 2, right? For 3, you get 0. And that take away 1 gives you the formula straight from the Pascal's triangle. So looking into this pattern and matching with the values, which are 1 less than the actual number of diagonals, we can clearly see that the formula could be derived straight away in the form of n minus 1 choose 2 minus 1. And of course, n has to be greater than 3 in this particular case, right? Now, we derived a different formula, which is n within bracket n minus 3. Do they really match? Oh, let's check it. So we have a new formula here, which is n minus 1 choose 2 minus 1. Now, if I expand this, I get n minus 1 times n minus 2 divided by 2 minus 1. And when you take the common denominator, right, so you get minus 2 in the numerator. And then when you open and simplify, what do you get? You get n squared minus 3n over 2, which is same as n times n minus 3 over 2. Perfect. So we got exactly the same formula. I've just written it in a different form. So I'm now saying my formula is n squared minus 3n over 2. It's the same thing as you can take n bracket and you get n minus 3 over 2 as your formula. Is that clear to you, right? So both are exactly same formulas. But see how simply we could use the Pascal's triangle to derive, just as simply we use the definition of choose 2 from n to derive. Do you see how simple it becomes? Now, let's look into the pattern rule. So many times we have to look at the pattern and get explicit formula from the pattern rule. That could be a big exercise at times, right? So in this particular situation, we think about again the diagonals. So if there are n sides of a polygon, we know that the number of diagonals will be 0, 2, 5, 9, 14, 20, 27, and so on, which is the second diagonal of Pascal's triangle. Okay, now to derive a iterative formula or explicit formula, we will follow some rules and regulations. So what we do here is we have all these odd numbers. Let's multiply by 2. Multiplying by 2 gives us these numbers. 0 times 2 is 2, 0. 2 times 2 is 4. 5 times 2, 10. 9 times 2, 18. 14 times 2, 28. 20 times 2, 40. And double of 27 is 54. Well, is there a way to connect the number of sides with the number which we have just got? Well, 3 times 0 is 0, 4 times 1 is 4, 5 times 2 is 10, 6 times 3 is 18, 7 times 4 is 28, 8 times 5 is 40, 9 times 6 is 54. And so we have a formula, n times n minus 3. You know the difference between 8 and 5 is 3, 9 and 6 is 3, 7 and 4 is 3. So the difference is of 3. It makes sense. In a triangle with 3 sides, no diagonals. Additional side, we have diagonals. So it makes sense, right? And so clearly, we have 2 times the number of diagonals is n times n minus 3. So the number of diagonals will be n times n minus 3 divided by 2. So that is how we can get an explicit formula for our case, right? So we have an explicit formula here. Is that clear to you? Now that is how you get to this. Now we'll look into the last method, which is the method of induction. Now, method of induction is an excellent method where, especially if you derive at some formula and you want to prove that that is the right thing, right? So we could actually follow a rule, which is when you're given that in this, as in this particular case, that we need to prove that using the method of induction, that the number of diagonals in n-sided polygon is given by the formula n times n minus 3 over 2, where n is greater than or equal to 3. This is what we need to prove. Correct. So the method is, one, we have to choose a number, the initial condition, right? That is the first thing, right? So initial condition. So in this case, we know if we have a triangle, which is n equals to 3, that the diagonal 3 or three sides has to be 0. That is what the initial condition is. So what we did here is we substituted n equals to 3. So in the formula given to us, as soon as I substitute n equals to 3, as you can see, you do get 0, and you know that that is true since triangle does not have any diagonal. That is perfect. Now the second step is that we'll take n or k as the value of n, and we'll assume that this is true. This makes the formula true. However, if I take the next item, k plus 1, in that case I have to show that is true. Then, in that case, for every k plus 1, it is going to be true. And that is how you prove your formulas, correct? So, we take k as a value. In that case, we now know that dk, that the number of diagonals when n is equals to k, will be k times k minus 3 over 2. So let this be true. Now the whole idea here is to show that when I take k plus 1 items, then replacing k with k plus 1, we get another simplified form that should be true. So that is the whole objective of doing this. So now let's do some algebra part, right? So let's try to again figure out the logic. So the logic here is we again have the same kind of a pentagon, but think about any polygon at this moment. Is that clear to you? Any polygon. So with k sides. So think about a polygon like, let's cut off here, right? So it could be a complicated polygon with k sides. Okay. And now a new vertex is added. So I'm calling this to be our new vertex, which is being added. Now, as soon as you add the vertex, then what happened? Well, originally we have dk diagonals, right? Originally we had dk. Now, what additional number of diagonals did we produce? Of course, one of the sides, which was an edge, has become a diagonal. So we have put this as one of the additional diagonals, right? The other one is, if there are n sides, we have two edges because that n gets adjacent. Vertices only give you edges, right? The vertex has to be more than one vertex away. So the two which are close by will not give you the diagonal, and so we have k minus 2 terms with additional number of diagonals. So in all, we have n. If we have n diagonals, in that case the additional ones are k minus 2 plus 1, which is k minus 1. So k minus 1 is the additional number of diagonals for an additional vertex. Now, we have to find the diagonals with k plus 1, and we know it is k minus 2 plus 1 in addition to what we had. What we had was the formula, correct? Which was true for dk, for n equals to k, correct? So we have that expression now. Now it's a matter of simplifying. So basically, just simplify this. K minus 2 plus 1, you could have written directly k minus 1. Take the common denominator of 2 and simplify. When you factor, you get the same result, which is k plus 1 times k minus 1 divided by 2. So you have shown that the formula works for k plus 1. And since it works for k plus 1 also, the formula is true for any polygon with n side. So for n-sided polygon, we now know our formula, which could be written in many different forms as we have seen here. It could be, n times n minus 3 over 2, or in expanded form, correct? So all these forms we could write our diagonal formula, and now we know that the diagonal number of diagonals will be n times n minus 3 divided by 2. So that becomes the formula. Easy way to remember is that the triangle will not give you any diagonals, so the result should give you 0 for that, and n minus 3 is a factor for that, correct? Correct. Now there are n points, and you are actually engaging two of them to make one diagonal. So n divided by 2 is the factor which gets multiplied to n minus 3, and that is how you could reason it out and make sense. Okay, so there are so many ways to do it. We have learned in this particular curriculum these four things: combination, the choice one, the Pascal's formula, the patterns rule, and the induction method of proving that your formulas are correct. And we have applied all these techniques, and I hope that helps you to understand and recollect all your learnings. That makes you feel better for examination preparation, and that's the whole idea. So thanks for your time and all the best. If you really want to learn from me, you can send an email at this particular address and we can get in touch and learn together. Thanks and all the best.